Okay, so we're going to look at a couple of problems from section 4.7. This is going to be optimization, so 4.7 is optimization. All these optimization problems, basically, there's going to be kind of 4 steps we do each time. Step 1 is get the equation that we're dealing with. Step 2 is set an interval for the equation that makes sense. Step 3 is find critical points. And then finally what we're going to do is we're going to find absolute max and min. And this will be like we did in section 4.2. So these are kind of the processes we're going to do. We'll do a couple examples first, and then we'll do a couple more to wrap the section up. And that'll kind of be it. So for example 1, we got a piece of wire of length L is bent into a rectangle. Okay. And we want to say what dimensions will produce the maximum area. Okay. So what they give us a wire of length L. So we got an overall wire here, it's length L. We're going to bend it into a rectangle. And I want you to kind of think, if we viewed the rectangle as to kind of like a 2 different shapes. So say one of them is along here to here, and the other one would be like down here to down here. Each of the lengths of those pieces would be half the length of the rectangle. So I guess what I'm saying here is, if we had the shape like this, top part shape is like that, the shape of this kind of shape thing here would be L over 2. And if the bottom part also was a shape like that, that would be half the overall length. So if we call this length of one of these parts here x, well, then from here down to here, that's a length L over 2. So if I take the length L over 2 and I subtract this part here that's x, this little height will be L over 2 minus x. Because basically we're saying if from here all the way here and then down there, if that's L over 2, and x of the units are starting here, scooting over to here, then, oops, let me turn on my little cursor to, oops. Oh, I guess it's not working. Okay, well, sorry, I guess it's not working. So we'll just say if we go from here to here, and that is that's x, then this distance from here down to here, that would be the total distance L over 2 minus the x distance there. So that'd be L over 2 minus x. So it's a lot of kind of statement to get the setup that we're working with. So now we're going to use that to generate the equation of the thing we're trying to maximize. So we got what our rectangle looks like. Step 1 is we want to get our equation. So the equation that we get would be area, which would be the length times the width of this rectangle. So we'd say that's L over 2 minus x times an x. And we could distribute that if we wanted to and say The area is L over 2x minus x squared. So now what we need to do is we need to think about, so we got our area function, we got our equation. So from our four little things, we got the equation. Next we need to think about what are intervals, how big could x be? The smallest x could be would be 0 units. And the biggest x could be if x went all the way out and we used the entire half the length, the largest x could be would be L over 2. So we have our boundary, we have our interval on the x's. So that's the second thing we had to do. We got the equation, got the interval. Now we're going to need to find the critical point. So to do that, we take the derivative of the area. So that would be L over 2, because the x drops, minus 2x. Critical points are where the first derivative is undefined or 0. The first derivative is never undefined for this type of equation, so we're going to set it equal to 0. L over 2 minus 2x equals 0. The negative 2x can come on over, so we'll get L over 2 equals positive 2x. Divide the 2 across, so L over 2 divided by 2 is L over 4 equals x. And this is our critical point. So the final thing that we got to do, now that we got our interval and we got our critical point, is we need to figure out who takes this equation here and who's going to maximize it. We could use either form. We could use the top form or the bottom form. So we're going to say who creates the maximum amount of area. So we'll say, all right, let's look at x and our area equation, see what our area function gives us back. We could be maximum at the endpoints of the interval, or we could be maximized at the critical point. So if I put 0 in here, I get L over 2 times 0, which is 0. If I put L over 2 in for the x's, so I'm plugging them in for the x's here and here. If I put L over 2 in there, then what I get is L over 2 minus L over 2, all that times L over 2. But L over 2 minus L over 2, that's 0, so I get 0 times L over 2, which is 0 again. If I put L over 4 in there, I get L over 2 minus L over 4. L over 4, all that times an L over 4. L over 2 minus L over 4 is L over 4. L over 4 times L over 4 is L squared over 16. So this right here is the maximum area. We need to read the question again to make sure that the way that we format our answer is what they want. They want us to say what dimensions will produce the maximum area. So the maximum dimension was when x was L over 4. So if x is L over 4, then that would be the length is L over 4, and the height would be L over 2 minus L over 4, which is L over 4 again. So we would say the dimensions that maximize would be L over 4 by L over 4 are the dimensions. We'll say the rectangle dimensions that maximize area. Okay, so we got x is L over 4, and when we plugged that into our rectangle, when we plugged L over 4 into our rectangle setup, we got the length was L over 4, and the height was also L over 4. So we generated a L over 4 by L over 4 rectangle. Okay, so that's first example. Let's scoot on over and take a look at the next one. All right, so for this example, let's see what we got. We are going to build a road joining a ranch to a highway that enables drivers to reach a city in the shortest time. So we will build a road from a ranch to a highway that will minimize travel time to a city. Okay, let's see, what else next? How should this be done if following things happen? The speed limit is 60 kilometers per hour on the road and 110 kilometers per hour on highway. So 60 kilometer per hour speed limit on road, 110 kilometer per hour speed limit on highway. The perpendicular distance from the ranch to the highway is 30 kilometers, and the city is 50 kilometers down the highway. So perpendicular distance from ranch to the highway is 30 kilometers, and the city is 50 kilometers down the highway. Okay, so first we're gonna go through and kind of draw a picture to help us visualize what's going on. So we'll say, okay, the idea here, we got a little ranch, so I guess we'll say like it's a little, I don't know, house with a windmill kind of thing. Something like that, I guess. So that's our ranch. And over here we got a city, so we'll just say something like that. Be our city, I guess. Okay, so the perpendicular distance from ranch over to, here's a highway. Perpendicular distance from ranch to the highway is 30 kilometers. And from here to here is 50. We're going to draw a road, so some diagonal road that will meet the highway at some point down. We'll call the distance down there X. And if that's the case, then the distance from here all the way out to the city will be 50 minus X. The speed limit on this road here, we said, was 60 kilometers per hour. And the speed limit on the highway is 110. So our goal is in this little setup here to figure out how far from the perpendicular distance here, how far should we have the meeting point where the road meets the highway. And again, we want to remember, we're trying to minimize time. So we're going to use distance equals rate times time, and we'll say distance over rate is time. And we're going to use that to generate our equation. So we'll say capital T of X, this will be the time equation, depending where X is. Okay, we should be a little careful here. This is kilometers, this is kilometers, this is kilometers per hour, this is kilometers per hour. So what I'm trying to get at here is distance-wise, this is X kilometers, this is 30 kilometers. This right here, this diagonal length, we can use Pythagorean theorem. And the distance on that is 900 plus x squared. So it's 30 squared plus x squared, the square root of that. It's that many kilometers. The 60 kilometer per hour is the speed limit there. So we want to make sure that we don't get that confused with the actual distance. And then this one right here, it's 50 minus x kilometers. The speed limit is 110 kilometers per hour. So let me scoot those speed limits kind of on up so that we don't get them confused with the distances. So we're going to take the distances, we're going to divide them by the rate. So we'll say, all right, the distance of the little dirt road was, or I guess we don't know it's dirt, but the distance of the road with the slower speed limit is 900 plus x squared. Again, how I got that, this is a right triangle, this side's 30. This is a right triangle, that side's x. And then you can use the Pythagorean theorem, a squared plus b squared equals c squared. Therefore, a squared plus b squared under the square root is c. Okay, so this is the distance, and then the speed limit over that is 60. We're going to add to that, so that would be how long it takes you to go along this diagonal line. Then we need to know how long does it take you to go from the highway down to there. The distance you travel would be 50 minus x. The speed limit of that region is 110. So this is our time equation. So we got our equation. We need to think about what are intervals that make sense for x in this situation. Well, x at smallest could be 0, where you just come straight down, so that'd be 0. And at biggest, x could be 50 miles over, where the whole time is just this diagonal road. So we got our interval. Now we need to find the critical points, and I'm going to algebraically rewrite this a little bit to make it a little cleaner for the derivative. So I'm kind of just algebraically rearranging some of the stuff so that when we take the derivative, it's a little bit easier to see what's going on. So I'm going to, divide by 60 is the same as multiplying by 1/60th. Square root of stuff is that to the 1/2 power. Plus out here, I can write this as 50 over 110. I know that reduces. I'm just going to leave it like that for a minute. And then this would be negative x over 110. But again, dividing by 110 is the same as multiplying by 1 over 110. So we can get it like that. Then when we go to find the derivative, t prime of x, have 1 over 60. The 1/2 comes down. We're going to use a chain rule. So it's 1/2. Leave the inner mess alone. All that becomes to the negative 1/2. Then we multiply it by the inner derivative, which 900 plus x squared has derivative 2x. The derivative of a number goes to 0, which is why I didn't worry about reducing that, is because the derivative is going to make it go to 0. And then out here, the derivative of 1 over 110x, the x drops and it leaves you 1 over 110. So a couple things. We can cancel the 1/2 and the 2. I'm going to go and kind of set this up to make it look nicer now. We have x up top. We have 60 down here. And since this all is to the negative 1/2 power, it's square root of 900 plus x squared. And then that's all minus 1 over 110. Okay, so critical points are where that equation here will be 0 or undefined. If this was a minus, we would have 900 minus x squared. Since squaring something always makes it positive or 0, we'd be able to get division by 0, so there would be an undefined. However, since this is plus, and x squaring something always makes it 0 or positive, this is going to be 900 plus some other value, so we're never going to be able to cause division by 0. So there's no undefines here. What we're going to have to do to find the critical point is we're going to have to set the whole first derivative equation equal to 0. And we're going to have to hope that that is solvable if we get a critical point. So let's see here. I'll scoot the 110 over. Oops, 110. I'm going to cross multiply, so 110 multiplies up here. That whole mess multiplies there. When we worked this in class the other day, I did not divide everything by 10 in this step, so the numbers got really big. So in here, I'm going to go through and divide both sides by 10, which will give us 11x equals 6 times square root of 900 minus x squared, and that'll keep the numbers a little bit smaller. So we're going to go through, and at this step, we're going to square both sides. So we say, all right, this will be 11 squared, x squared, 6 squared, and square root of that squared. 11 squared is 121, x squared is x squared, equals 36 times. The square peels off the square root, leaves you 900 minus x squared. 36 is going to distribute, so we get 121x squared equals, let's see, 36 times 900 is 32400 minus 36x squared. Add the 36x squared across, so 121 plus 36 is 157. X squared equals 32400. To get rid of the well, I guess we can't get rid of the square yet because we got the 157. We need to divide that across first. And then finally we can get rid of the square by taking x equals plus minus square root of this. Now in our drawing that we did here, if x was a negative value, it would be going over here. And we can see that that's not going to maximize the distance. That's going to add on extra time. So that'll never lead to the minimum time. If you start going the wrong way, then tracking back, that'll never be faster than just going the correct direction. So that's going to allow us to throw the negative choice out here. And then we'll type this in and see what we actually get. So we get square root of 32400 divided by 157. That is 14. Let's see. Whoops, hang on. I've got an issue with what I typed in here. So made a mistake somewhere along the path here. Let me see. There, 11 squared is 121, right? Let's see. 6 squared is 36, should be. And then, let's see what oh, here's where I made a mistake. Okay, so, yeah, I worked this out with the other class when it was 19 something and I got 14. So here it was 900 plus x squared. So it still needs to be 900 plus x squared, still needs to be 900 plus x squared, needs to be this plus that. Means whenever I go to do this, let's see, this number is going to change and this number is going to change. So instead of adding 36 across, I need to subtract 36. So 121 minus 36 is 85. And then we divide that 85 on over. So we end up down here with this all divided by 85. And hopefully that's 19 point something or other, like we worked in class the other day. So square root of 32400 divided by 85 is 19.524. And x is a distance, that's kilometers. So let me check with the book and make sure that we've got the same number. They have 19.52. I'm keeping an extra decimal. So yeah, everything's lined back up now. I just made a mistake where I switched the sign from here to here by accident. So now that we got that, we need to, we're trying to minimize the time. So we need to go through and we got 0 for an endpoint, 50 for an endpoint, and 19 point whatever for a critical point. So we're going to build a table with x and the times it takes. So we had 0, 50, and 19.524. I need to plug these values into the time equation. So I'm going to use this form right here. I'm going to put that into my calculator so I can just update the values and get what the corresponding times, when you give it an x, get what time it gives you back. So let's see what happens here. Okay, if we put 0 in, it's going to take 0.955 of an hour. If we put 50 in, it's going to take 0.972 of an hour. We put 19.524 in, that'll take 0.874 of an hour. So this right here is the minimum time. This minimizes the time. So we would say the road should meet the highway 0.524 kilometers from where, I'll say from the perpendicular, from where the perpendicular distance meets the highway. Okay, so basically we're saying there's here's your, here's the ranch right here, here's the city. So here's where the perpendicular distance meets the highway, and the road should come in, and 19.524 kilometers down from the perpendicular distance is where the road should meet the highway. So that should be just reading this over again just to make sure we're answering it exactly how they want it. They haven't really specified, like, in terms of a dimension. They just say how to do it. So this explains how to do it. So we'll stop this part of the video here and get the rest of it in the second part.